Hello everyone. In this video we are going to see the operation of Cascode current mirror, and then we will perform the DC analysis and transit analysis for the Cascode current mirror. So basically what is meant by current mirror? Current mirror is nothing but we are going to copy the input current to the output side. So where we will use the current mirror? So in the current steering circuits we will use the current mirror circuit. So what is meant by current steering circuits? The current steering circuits is nothing but copy the reference current to the all the subcircuits, that is called current steering circuits. So what is the drawback in the basic current mirror? In the basic current mirror we didn't consider anything about your channel length modulation. Here you can find a lambda factor, the lambda is 0. So in the basic current mirror we didn't consider any channel length modulation, and as well as your VDS. Suppose here in the output side I have another circuit over here. So due to the circuit here, the voltage will get changed in the output side. Once voltage gets changed, the output also gets changed. So it will not be equal to the input current. So this is the drawback in the basic current mirror. So to overcome that one, we have introduced an cascode current mirror. In the cascode current mirror, we have an M3 and M4 which follows current mirror, and likewise an M1, M2 also forms in current mirror. So whereas here, to make your M4 output current to stable, we have used another current mirror over as an M1 and M2. So here you can see the M2 is twice of your M1 in terms of width and length, and M4 is twice of your M3 in terms of width. You can see here NMOS1. The NMOS1 is a name for M1. So the NMOS1, the width is 10 micrometer, and for NMOS2, the width is 20 micrometer. And for NMOS3, the width is 10 micrometer, and for NMOS4, the width is 20 micrometer. And then here in the cascode current mirror, we have considered the channel length modulation. So I have used 0.04 as a lambda factor, and where Kp is nothing but your mu n Cox, and then where gamma is as nothing but your the bulk threshold value. This is the bulk threshold value. So you can take it as a 0, and you can take it as a 0.4 also. So now let us perform DC analysis. So to perform DC analysis, go to simulate and edit simulation command, go to DC sweep. I want to vary the voltage source. That's named as a V1, and then I'm going to type of sweep as linear. The start value is going to be 0, and I want to sweep the voltage source to the maximum value of 5, which increments by 111. So now I want to measure the what is the output current at particular voltage in terms of 2, 3, 4. So now to measure that value, so we have used a statement spice directive file dot measure, MES is measure, and then we are going to measure the IREF. So what is meant by IREF? So here I have named it as a IREF, so I'm going to give the same name as a IREF. And what I'm going to find? I'm going to find the ID of M1, the drain current. The drain current, this is the drain, this is a gate, and this is source. I'm going to find the drain current of M1. So find ID of an M1 when voltage is equal to, when V1 is equal to 2. So likewise we can give the statement. You can see here the current mirror also we have used, and the time is equal to 3 milliseconds for the transit analysis. So now we will perform this. So the output is add trace ID of M1, M2, M3, M4. These are the 4 output currents. So here this is the output current. You can see here ID of M3 and M4 1 pair, and M1 and M2 1 pair. So M3 and M4. First you will see the M3 and M4. M3 is red. You can see here the current is linearly increasing. You can find the area of M4. So since the width is twice of the M4 width is twice of your M3, you can find the increase of current linearly compared to the M3. When the both M3 and M4 same width, you can find the same current. Likewise, M2 is twice of your M1. So M2 is blue color. You can see the M2 is very much high current compared to the M1. M1 is black. So the M2 is twice of your M1 in terms of width. So that's why you can find the M2 current is very much larger compared to the M1. So this is the basic DC analysis. So you go to view and then you can find a Spice netlist over here. The Spice netlist is nothing but where it will convert the circuit diagram into a basic coding. So and then we can use here, you can go for transient analysis, transient. So I want to execute for 5 milliseconds and 0.1 milliseconds it will increment. So now here I can use a statement called when time is equal to 3 milliseconds, I want to find the what is the ID. Go to Spice directive and paste it here. So I have pasted I have IRF. I need to find the IOT. I am going to find the ratio. What is IOT by IRF? So now I will perform. Let me close it. Let me run again. Add trace ID of M1, M2, M3, and M4. Sorry, I didn't give the voltage value. So the V1 should be 5. V1 should be 5. Sorry for that. So now let me run it. Add trace, and then you can find ID of M1, M2, M3, and M4. You can find here. This is a transient analysis. You can change your bottom to 0 and top level to 10 microamps. So you can find over here. As I said earlier, M3 and M4 is one pair. So for M4 is twice of your M3. So you can see here M4. This is the M4, and then M3 is red. So you can find the current has been doubled. Likewise, M2 is twice of your M1. M2 is blue color. The output current is around 8.8 microamps compared to the M1, which is 4.4 microamps. So now we can go and find the Spice error log. We can find the what is the current value at 3 milliseconds, 3 ms, the 4 into 10 to the power minus 6, and for ID of M2 in the output side we have 8 into 10 to the power minus 6. So the IR by IRF is equal to 2. So whereas here we have used an parameter is equal to 2, which is twice. So that's why the output current also it has been doubled. So this is how you can perform your DC analysis and transit analysis for the Cascode current mirror. Thank you for watching.